So we were discussing the nonlinear modeling of reinforced concrete structures, and in that primarily we are focusing on two nonlinear modeling approaches. One is the lumped plasticity approach, lumped plasticity. It is also sometimes referred to as the concentrated plastic hinge approach. So I just refer to this as the plastic hinge approach, right? Second approach is the distributed plasticity, in which the nonlinear effect is assumed to be located at a certain length or full length of the element. So that is distributed plasticity, and we are actually using fiber modeling approach to distribute plasticity along the length of the element. So this is fiber approach. So these are two basic approaches, right? The main difference is that in first approach we assume that nonlinear action can be lumped at certain locations only, and in between those locations we assume elastic element. For second approach, we distribute nonlinear action along full length or part of the length. So we will be focusing on RC beams, RC columns and RC shear walls. These three elements, nonlinear modeling of these three elements. So what I primarily focus in this particular session or next one or two sessions is the lumped plasticity approach for RC beams, right? And then we will directly go to fiber modeling approach or distributed plasticity approach for RC columns and shear walls, right? So although we can model RC columns and shear walls using plastic hinges or lumped plasticity approach, but we will not focus explicitly in this particular topic, right? So RC beams using plastic hinges, lumped plastic hinges, and RC columns and shear walls using the fiber modeling approach, right? So once you focus on these three, you can say, topics or aspects, you will be able to at least develop the nonlinear model for your example structure, right? So again I repeat that you can model all these three elements either using plastic hinge, all of them, or using distributed fiber approach for all of them, but you can sometimes use one approach for one particular element and another approach for other elements, right? So for columns and shear walls we focus on fiber modeling approach. For beams we just directly use the lumped plasticity approach, right? So let me directly go to the point where we left last time. We discussed that there are two types of plastic hinges available in ETABS. One is the uncoupled type, in which you use the force deformation behavior or action versus deformation behavior in an uncoupled form only for a particular degree of freedom. And these hinges in ETABS are located here. In section properties you can go to wall frame nonlinear hinges, and then you can define a new hinge, and then before actually giving its force deformation behavior or action deformation curve, you first have to select the type of hinge. So if you are only interested in modeling reinforced concrete beams flexural action, then go for moment M3, right? If you define this kind of a hinge at two ends of the beam, the flexural nonlinearity will be captured using these two hinges, but the other 5 degrees of freedom, for example shear, torsion, they will not be affected, they will still remain elastic, right? If you want to account for shear nonlinearity in a beam, go for shear V2, shear hinge. V2 is the primary shear in a beam. If you want to go for plastic hinge modeling of columns, lumped plasticity approach for columns, go for this interacting PM2 M3 for a 3-dimensional column which can have a moment in both directions and have an axial force as well, right? Similarly, you can also select your relevant or applicable type of hinge depending upon what action you want to convert into nonlinear, right. So, uncoupled hinges, 6 of them, they only affect one particular degree of freedom at one time, other 5 remain elastic by default, right. Coupled hinge affect more than one degree of freedom. For example, this PM2 M3 hinge, this one, let me make it big here, this one, interacting PM2 M3, this affect you can say both moment degree of freedom and the axial load, right. So, for RC columns you will be going for this option. If you want to model an RC column using fiber modeling approach, you should go with this last type of hinge, which is fiber PM2 M3, right. So, these two which I encircle now, they are for columns, but the first one, the top one, will be using the plastic hinge, concentrated plastic hinge approach. The last one will be using the fiber modeling approach, right. And please remember that the difference between them was that in fiber modeling approach we define the nonlinear action deformation behavior right at the material level, the fundamental level, in the form of stress strain curve, and then that stress strain curve have its effect on the cross sectional stiffness and then member stiffness and then full structural stiffness. In the plastic hinge approach, we directly define the member behavior. So, here we will be defining directly the moment versus rotation curve to account for flexural nonlinearity, but for fiber approach we will be defining stress versus strain curve. Parametric concrete and steel are there which you can use to just give few inputs for certain parametric cross sections, and then the program has the capability to develop the hinge properties. But the hinge property will be different for each type of hinge. For moment M3 type, this one, the hinge primarily should have a moment versus rotation behavior at that location where you will assign that hinge in the model, right. For interacting PM2 M3, you should not only define moment versus curvature behavior, but now you know that that moment curvature behavior is dependent on the axial load level also. So, moment versus curvature, at the same time you also have to provide here the PMM interaction surface, which tells the program that what will be the moment curvature behavior at a certain level of axial load. So, the program will be using a kind of a variable moment rotation behavior for column that depend on the level of axial load on that column, right. So, capacity is defined by moment rotation curve for an uncoupled beam hinge M3 hinge, but it is defined by the complete PMM surface and moment rotation curve at the same time for a column or interacting PM2 M3 hinge. So, in plastic hinge approach, ASCE 41 is our primary reference, right. So, ASCE 41 approach for nonlinear modeling is actually the plastic hinge approach, right. So, let me write it here. So, it follows that moment rotation plastic hinge approach ASCE 41, that whole standard. It is actually meant for the retrofitting and evaluation of existing buildings, but it is also applicable for performance evaluation of new buildings, right. So, if you want to conduct the performance evaluation, performance based design, ASCE 41 guideline can be used. So, this guideline primarily adopts the plastic hinge approach for nonlinear modeling of reinforced concrete elements, right. So, it does not talk about fiber modeling approach, but the input required for fiber modeling approach is relatively easier to get, because you only require the material stress strain curve, which you can get from the lab testing easily. But full member level behavior, moment rotation curve or other behaviors, that you cannot directly test for each type of beam. So, you require a guideline like this, which based on extensive testing will guide you what moment rotation curves or what action deformation curves you should use for your plastic hinges. And not only it gives the curve for different elements, it also provides you the acceptance criteria. It also provides you 3 markers or capacities corresponding to the IOLS and CP, 3 standard performance levels, and it gives you the plastic rotation corresponding to that, so that you can input that in program, so that program knows what is the capacity corresponding to different performance levels. So it can divide the demand with that capacity and calculate a DC ratio for each performance level, which after the analysis you can check systematically one by one to convert your analysis results into physical feel of the structural performance, right. So ASCE 41 is our primary reference for plastic hinge modeling, a modeling approach in which we directly provide the member level action deformation curve. So as we have discussed last lecture also, that it not only provides us the modeling parameters small a, small b, small c, which we can use to construct the moment versus rotation curve or any action versus deformation curve for our any element, because it provides detailed tables for different elements, and those tables provide us these parameters which we can use to construct that action deformation curve. And also it provides us the acceptance criteria, that 3 capacities on those curves corresponding to the 3 performance levels, right. So it will give you the deformation level corresponding to IOLS and CP. These are capacities or acceptance criteria, as the name indicates that these are the numbers which are acceptable for a particular performance level. So if I say that 0.02 radian is my IO level acceptance criteria, it simply means that any rotation of a particular beam or plastic hinge greater than 0.02 is not going to fulfill my IO level requirement, right. So the structure is not going to pass my immediate occupancy requirement or performance level if its rotation is more than 0.02. So these numbers, acceptance criteria, they are literally kind of converting your analysis results into performance, into physical description of performance, right. So for beams I will show you that table, but the general procedure for ASCE 41 is, for each type of element, first it defines a generalized force deformation relationship, action versus deformation relationship. So on y axis you have action that is normalized by the yield capacity corresponding to that action. So it can be moment versus rotation theta, it can be torque versus twist, it can be shear force versus shear deformation, depend on what type of nonlinearity you want to include, in which particular action or degree of freedom you want your structure to behave as a nonlinear structure, right. So the most common example which I can keep on giving every time is beam case, where you want to include flexural nonlinearity, which means you want to have an M3 plastic hinge, right. In ETABS terminology, M3 plastic hinge. Let me quickly go back, exactly see what ETABS call that particular plastic hinge. Moment M3. So moment M3 is a hinge type which you will always include in your beam to account for flexural nonlinearity. So this moment M3, this is the very simple kind of plastic hinge which is uncoupled type and which only requires moment rotation curve at the 2 ends of your beam to be given as an input. So ASCE 41 provides you the action versus deformation curve in the form of small a, small b and small c. These 3 are called modeling parameters. If you calculate the yield capacity, yield moment capacity my, then you can plot this full curve if you are given with small a, small b, small c, right. So, the ASCE 41 table will guide you that what is the plastic rotation between first yield point and the ultimate point. It will guide you what is the plastic rotation between first yield point and the last point of the curve, and it will also tell you how much is the residual strength you should expect in your beam. Obviously, this My, which is required to construct the y axis of this curve, is the function of amount of steel of your beam, is the function of dimensions of your beam, and Fc prime, Fy, clear cover, everything. So, all the material properties and cross sectional properties of your beam will be used to calculate My, and then at that particular My your curve is going to yield, and actually you will require other A, B and C along with My to construct that complete curve. So, A, B, C are modeling parameters, and also the ASCE 41 provide us the IO level plastic rotation, LS level and then CP level. So, it will give you 3 rotation values for your M3 beam, which are corresponding to IO, LS and CP. So, not only it will give you the force deformation curve, it will also give you the IO, LS, CP capacities in the form of plastic rotation, right. So, if this was shear force versus shear deformation curve, the IO, LS, CP will be in the form of shear deformation. Currently, for moment 3 M3 plastic hinge, it will be in the form of rotation of beam. So, IO, LS, CP will be in the radians, right. So, then there is some customizability also. You can modify using some parameters this backbone curve to account for a trilinear kind of a behavior also. This is the default action versus deformation curve, which is available in Perform 3D, and it is more general compared to ASCE 41. I mentioned last time that ETABS is specific to ASCE 41. It follows ASCE 41 terminology, and everything is according to ASCE 41. Perform 3D is a more general program. It doesn't comply with, it doesn't exactly follow ASCE 41. So, it provides you more control on the curve shape, right. So, if there is a specific kind of behavior between your action and deformation which cannot be captured by the curve given by ASCE 41, Perform gives you that freedom to customize it in a number of ways. For example, the strength degradation, strength loss, it gives you the feature to include strength loss or not include strength loss, and then several other features to customize the shape of this curve. So, Perform called it as YULRX curve, right. ETABS call it as, I think, ABCD following ASCE 41. So, Perform calls it YULRX, Y yield point, U ultimate point, L from where the strength loss start, R is where the residual strength retains, X is the last point beyond which there is no physical meaning of continuing the analysis, right. So, now you already know what are the features or what are the inputs required to a plastic hinge which is representing nonlinear action in a particular degree of freedom. So, this is that table, RC beams, table 10-7 from ASCE 41. So, you can see that it asks for few inputs first. Let me highlight them. This factor is rho minus rho prime over rho balance. So, we will not go into their detail, but this is a parameter related to the amount of steel in a particular RC beam. Then your transverse reinforcement, whether it is C or NC, C means conforming, NC means non-conforming, and I will show you in next slide what it actually means. The last thing you require is this factor V over BD under root FC prime. So, BD are the cross sectional dimensions, FC prime is the strength, expected strength of the beam material, and V is the shear force in that particular beam at the time of plastic hinge formation, So, all of these three columns first you need to calculate for your beam, then you can enter in that table, and let us say that you know all these three parameters, and finally let us say this is the first row which is applicable to your beam. Let us assume for the sake of simplicity here. So, once you select your beam, your particular row, then you can pick small a, small b, which are the plastic rotations. Small a is defined as the rotation from yield point up to ultimate point, and small b is from yield point up till the last point of moment rotation curve, right. Small c is the residual strength ratio. So, it is the ratio of strength remained after degradation to the actual yield strength. So, 0.2 means 20%. So, it will be like this. If I follow this first row, I should be able to develop this kind of a behavior for my beam, in which on y axis you should have a moment, and at this particular location this is my. This my you should calculate yourself, right. It will be the function of fc prime, fy, amount of steel and everything. You can use some simplified method to calculate my. It can be Whitney's approach also. So, my you should calculate yourself. This is the moment capacity of your beam. From my onwards, your beam will yield, and this distance will be small a, and this distance, last point distance, will be small b, and this small height is actually c. Actually, it is not exactly c, it is 0.2 times or c times the yield point my, right. So, if my is 100 and c is 0.2, so this height will be 20, right. So, using small a, small b, small c and my, you will be able to calculate this m theta curve for your beam, right, and then that curve you can directly define in E tabs and define plastic hinge at the corners of your beam, ends of your beam. And in the same row you are also given with IO, LS and CP, and they are in the form of plastic rotation angles. So, small a was 0.025 and IO is 0.01, which means IO locates somewhere here, right. Similarly, LS is 0.025, which means LS is actually this point where you have this last point of curve, and CP is actually 0. This LS is 0.025, which means it is exactly at A, right. So, this is LS, and then CP is 0.05, which corresponds to B, which means very last point of this curve is actually CP, right. So, this whole row will guide you to plot that curve, and then three capacities corresponding to that. So, you can use this table, and then you can define plastic hinge in E tabs if you follow that. But obviously, you first need to calculate these three parameters in order to pick your values, right. So, if you see, first is the condition beams controlled by flexure, and then beams controlled by shear. So, mostly if your beams are designed, their design is controlled by flexure, behavior is controlled by flexure, you will be actually following these ones. There can be certain deep beams which are controlled by shear. In that case, you should follow these two rows. And then there is a third condition also, beams controlled by inadequate development or splicing along the span. You will see that for beams which are controlled by shear, the capacity in the form of plastic rotations is lower. Beams which are controlled by flexure, they can be allowed to go more in nonlinear range. So, their small a, small b, small c will be higher, which means they are more ductile, right. Similarly, within the condition 1, there is a thing called transverse reinforcement, and it is I think in next few slides I will show what it actually means. You can even read it here. Conforming means that there is a spacing requirement if it follows that if the spacing of hoops are less than d by 2 within the plastic hinge region at the ends, then it is conforming, and there is a second condition also, if it is fulfilled then it is conforming. So, and if the spacing requirement is not fulfilled or any of the two requirement is not fulfilled, it is non-conforming. So, you will see that if transverse reinforcement is non-conforming, the capacity is less, right, small a small b is less, right. So, a beam which is having a good shear reinforcement, closely spaced shear reinforcement, will have a larger small a small b, which means more ductile behavior, right. So, the complete moment rotation curve is giving us the ductility also for our beam, right. So, for a beam which have a non-conforming you can say transverse reinforcement, it will not have large plastic rotation. For example, if other two conditions are kept constant, less than 0, less than 3 and conforming, small a 0.025, but if again less than 0 and less than 3, but now the shear reinforcement is non-conforming, the capacity is reduced to 0.02, right. So, which means that for conforming beam the behavior may be like this, but for non-conforming beam the behavior may be like this, right. So, the small a small b is less for non-conforming. Same is the case for IOLS CP values, they may be less compared to the conforming beams, right. So, now the whole discussion should actually boil down to how we should actually get these 3 inputs required to enter in that table, because once we know how to use that table, beams plastic hinge modeling is done, because now you get all the inputs required from this particular table for beams. So, just to give you an idea that what these numbers physically look like, because see, if our action deformation curve was stress strain curve as we have in fiber modeling approach, then each point on that action deformation curve we can make a picture in our mind how the damage looks like, right. So, we know if we plot a stress strain curve, what is the concrete, how it look like at this particular point or how it look like at this particular point. So, just to give you idea for this full member level behavior, see, this is the rotation, this is the condition of your beam when its end rotation is 0.01 radian, right. So, this beam is subjected to some load, and then end rotation means that if this is your beam, let us say here this is your beam and this is the deflected shape, end rotation means that if I have a tangent of the deflected shape at the end, its angle with horizontal is that rotation, end rotation theta. So, 0.01 means almost no damage, 0.02 is some cracking starts, you can see here, maybe here and here, 0.05 significant damage, 0.06 complete damage, right. So, just like you have an intuition about the material strain that 0.003 is significant damage or more than that is significant damage, here you can make an intuition about the plastic rotation, right. So, 0.01 is almost intact, 0.02 is some minor cracking, right. So, now go back and see 0.01 is this number, let us say, and actually check IOLS and CP. 0.01 is IO, which means no cracking, and mostly it is even less than 0.01. Here the number is mostly 0.02 and 0.025, which means minor cracking, and then 0.05 or some other number which corresponds to significant cracking, right. So, using these kind of test results, you can develop an intuition about these numbers also, right. How much rotation is more rotation, how much rotation is less or not significant. And this kind of table in ASCE 41 is not only available for RC beams, it is available for RC columns. It is available for RC columns for circular and spiral reinforcement, for rectangular RC columns. It is available for steel members. It is available for shear walls and some other type of elements. So, the basic idea is same: small a, small b, small c, IO, LS and CP, IO, LS and CP rotation values, these 6 numbers will be coming from these kind of tables, using which you will construct your action deformation curve in respective degrees of freedom, and then give it as an input to plastic hinges, right. So, this particular table is for RC columns which are circular. So, instead of tabular form, here you directly have an equation for small a, small b and small c, and IO, LS, CP, the numbers are given. They are sometimes in the form of dimension of the cross section. So, but ultimately using this table you should be able to pick 6 numbers or calculate 6 numbers for your given column, right. Another table for spiral reinforcement, then RC beam column joints, right. So, for joint again plastic rotation A and B, residual strength C, and then IO, LS and CP they are given, right. So, depending upon different input things, you will enter in that table and pick your 6 numbers, construct your action deformation curve. So, this is the table for two-way slabs and slab column connections, same thing A, B, C, IO, LS and CP. So, please keep that generalized force deformation curve in mind, right, and all you need is these 6 numbers for your any element if you are following ASCE 41 approach, right. So, once you have these 6 numbers for all elements, then define them as plastic hinges.